was a 33, so if you didn't do as well as you would hope, don't worry too much. No, 33. So,
that makes slightly more sense.
All right, I'm going to call out names like two at a time. If you can come up and tell me which one of the two you are. Vish and Biljit. Sorry? Biljit. And Hamza and Ray. Okay. Lawrence and Bryce.
Bryce. Thank you.
Will and Anya. Chance and Shurya. Alex and Chris. I think I should know this. There's only one of them.
Yeah, I'm not.
Teo and Riley. And Juwon and Max. No, what's your...
Like the second time. Curry?
No. I'll check the rating box. I'm pretty sure I didn't consider it. Maybe I did.
Does anybody have two?
You might be stuck with the homeworks, which I didn't get around to, so
Okay.
I'll get that back to you on Thursday.
Okay.
Sorry about that. But we're going to go over the answers as well, so you can let me know if I misgraded anything. All right. So, problem one. You're an avid Starbucks chess player, and 5 games is not enough. You need 5 more free games, and you're not going to pay for it because that's why you're taking a hacking class. So the common confusion on this problem was you can just release an IP from the router. This isn't for us. So the issue with that is that the chess website sees the router's IP address regardless of what your private IP is. So this is your chess playing laptop. This talks to the Starbucks router, which NATs your laptop and then talks to the chess site. So chess.com is always going to see the Starbucks router unless you tunnel your traffic through the router out to some cloud or to a home VPN or something like that, where the chess site will actually see a different IP address. All right, does that make sense? Cool. Problem, yeah.
Yeah, so I assume that the chess.com server is hosted within the Starbucks local intranet.
Oh, like it's running on the Starbucks net? Okay. I'll reread the question. Bring it up after class and I'll look at it. But...
Yeah, I made the same assumption.
Okay.
Yeah.
You might want to bring that up to Professor Black then, because I don't know how he presents it. Yeah. So, okay. Yeah. Hang on to your quizzes until Thursday and bring them up because I don't want to make any like big decision on like changing the problem statement. But yeah, sorry. Yeah, that's fair. So
say they're checking your IP. What else would they see besides your external IP?
All right, problem 2. This one kind of sucks. There's no real partial credit. I tried to give partial credit if it seemed like you got everything right except for the flag. But if it was a little more than that, there's only really one right answer. So and it kind of sucks because this is really more of a memorization thing. I don't think I understood this until the web portion where you use this like every day to contact the server. So -L, it's opening a local port, 8888. You're talking to, or you're opening it to Foxy, port 80, and you're SSHing to Moxie. So the SSH command is always just going to be the last thing, or whatever your server is, and then all of the magic in here is the actual port forwarding.
So what would be the, what would you use for like one, if you were going to do SSH for one?
Sorry, for problem one? Or
Like you could use SSH.
oh yeah, I'm sorry,
Through
I
Moxie
didn't
for one.
go with the right answer. Yeah, so something like this would work because if you're SSHing through Moxie to, let's say this is the chess server, you're SSHing through Moxie, so Foxy sees the other end of that tunnel, so what's going on. Or if you use,
So the only difference is just switching out.
yeah, you need to change, somehow you need to change the external IP or the source IP that the chess server sees. So as long as you're changing anything internal to the router's IP is still going to be the one talking to the chess website.
So the only thing different in that command though is changing Foxy to chess. If you wanted to go to chess.
Exactly, yeah. So this is going to be where you're SSHing to. This is like your proxy, and this is your destination block. If we do the same thing, but this becomes an R, this is opening a remote port that's proxying things locally. So this, I'm gonna have to look up the actual command for that. Remote socket. This becomes a remote socket. This becomes host. And this becomes host port. So if you did this with the -R, you're opening this port on Moxie and forwarding everything that connects to that to Foxy at 80. So you're kind of doing it, everything's still going here, but to get there you have to connect to Moxie. You're not going to be able to proxy this connection because I think the problem says you can't see the Foxy web server because it's not public, right? Okay. Any questions on the first two? Okay. So 3 was definitely the hard one. Yeah. So you've got one command, or rather, you can get one program to run. How do you get someone to give you permanent and irrevocable access? So this is a little more complicated than copying a shell, because what's special about the shell on Raisin, first of all?
Doesn't drop privileges.
Exactly. So when you run something, when you run a shell program with either of these, set UID or set GID, modern shells will drop your privileges because that's been a big problem in the past, security vulnerability in the past. Fortunately, there's a pretty easy way around it. It's a little more complicated, but if you write a binary wrapper that invokes a shell, it gives you the ability to raise your permissions so that you can't get dropped out of your elevated permissions. So the way that works is let's say you have 2 programs. The first program is just a C program that you then compile into a binary. This calls something like set res UID to go. So you know Gullible's UID because it's in the Etsy password file. What's your name? Sorry? So you have Gullible's UID because it's in here. If you wanted to make this more dynamic, you could just have this, you could have like a get EUID or get something like that. Yeah, it'll be a get EUID and set this to that. But what this does is when this is called, assuming you have permissions to do this, so the only what stops you from being able to call to this line?
Well, at least one of them have to be Gullible's
Right.
UID.
Exactly. So what the shells do nowadays is they check if effective and real are the same. And if they're not, it's assuming that you're trying to do something nasty and it just drops you to the lowest permission. Or I think it drops you to real, so that if you end up getting a shell that calls raises your effective, you can't do anything nasty with that. But if we can get this to run before we call a shell, it could be bash, it could be anything because we've raised our permissions, then we're good to go. So this is going to be our irrevocable and permanent access to our account. What else do we need to do to that program to get our to get it set up?
Set UID.
Exactly, yeah. So we need to shown and chmod this program to owned by Gullible and set UID or set UID on. So we have some malicious program. When they call this calls shown Gullible and chmod user plus set UID. And now anytime we call this program, we get a shell with Gullible. Does that make sense? So a couple, if it doesn't, please let me know because I'm going to keep going, but okay. So some of the problems on this, the most common one was either a private key, SSH private key, which I can understand that's kind of been beaten into you guys with it being problem 1 on both homeworks so far. So I get why that feels like it's being harped on, but that's not irrevocable, right? So there's no way to keep Gullible from logging back into their account and just dropping it. A lot of people were talking about dropping Gullible out of their user group. That might be a misconception with users and groups. So a user is always going to have their user ID. So if you're Gullible and group Gullible, you're always going to have your user ID. So no matter what happens, I don't think you can get pulled from your group either. I think that that's a default. But even if for some reason, let's say that you use your temporary privileges to change the group and then like drop permissions on user, so this becomes something like that on their home directory. First of all, having access to their home directory doesn't give you access to their account, just whatever they put there. And secondly, they're always going to be the user that owns this directory, so they can always chmod it back or chun it back.
How do you, if those are the permissions of that directory, how do you change? How would they chmod that directory then?
The only problem that I see is if you can't log in. You're going to be able to chmod it because you're the owner. The owner always has the ability to.
Are they the owner right now?
So,
no.
Let's. I don't know how I'm going to be able to give an example, but yeah. So if the directory looks like this, so D for directory, nothing for user, read, write, execute. Then nothing again. the user is always going to be gullible.
Pretty sure that's not.
So maybe you could change the user goal. Sorry? We're talking about the home directory, right?
Yeah, I think didn't John do an example where he's like,
That was part of it, where there was like an SSH key was part of the whole thing, which is why, like, I thought that was part of the answer too, so I'm a little.
well, I guess I think he did one. He's like, you can actually drop yourself out of this, and you would think like, I think he said like, you could have permissions for like the everyone group, and you'd be like, aren't I everyone? And you're not considered every. Like if you don't have permissions as like the user here, like, you don't get access to it even if you're the owner. I think.
Well, if you change the permissions like that, and you were the owner but not part of the group, you wouldn't be able to CD into it or read and write it, but you could still chmod it because you were the owner.
So the problem, the only problem, yeah, so that's correct if you're, as long as you're on the system. The problem that I see is if you don't have, so if someone malicious changes this, the malicious could also potentially change the owner of this directory, which would screw everything up. Because yeah, they have access to do that, but even if they change just the group and they change this, I don't think Gullible's account is going to be able to read this when they try to SSH in, unless SSH is running its root and gets to the same keys. I'm not fully sure on that. If you think that your answer, yeah.
Isn't the point that you're supposed to be able to like create stuff as that user? So like if you had that shell, you'd be this solution allows you to modify stuff as part of their group, but the files that you create aren't going to be like files, Gullible's files.
Yeah, so this changes, you could recursively call chmod and chown on everything in their directory and then just like destroy their account, but you're not actually getting access to their account, which is kind of like the core part of this problem. If you think that your answer gets part of the way there, I try to be more or less consistent on this problem, and if you weren't on the track, on this track, then I didn't give partial credit, and I apologize. This is a really harsh grading, and I feel kind of like an asshole. But if you want to bring it up with John Black and argue your case, go for it. There were definitely some answers where you would get permanent access, but it's not irrevocable, and yeah, I think the core of the problem is getting a shell that owns Gullible's account, but that Gullible can't do anything about. Yeah.
So in class, you had also discussed that somebody last semester, or at some point, had copied, had copied, just straight up copied the bin sh, set permissions so that they could execute it, and then also set the set UID bit, and that had worked.
So why does that work, and why does that only work on Razor?
Because you don't drop permissions.
Exactly, yeah.
So that's like, would that not?
That's true, and that's fine on Razor, but this problem, correct me if I'm wrong, but this problem explicitly says Moxie is going to drop your permissions if EUID and RUID are different, right? Yeah. So yeah. But yeah, that did happen. I'd encourage everyone to try that in the future, and I would also encourage everyone to close your listeners, close your server listeners when you hit the problem when that happens. But it's kind of a cool little trick. Has he gone over that in class? I don't know if, I don't want to like ruin someone's day if they get there like last. Okay, does this make sense? Does anyone have, there was one cool solution that was interesting was remove their private key, add your private key, and then change their password to something really long so they can't brute force it, which was kind of clever, but you need their password to change their password, which is the pitfall there. But that was kind of unique and clever, so kudos. All right, any other questions on this? Okay. Yeah, if you feel like the lecture kind of like misled this question or something he brought up, definitely bring it up to him. I had a lot of room for partial credit on that one. that was pretty harsh. Okay, problem 4. This looks hopefully somewhat reminiscent to homework 0, the first one. So pretty much everyone got the first parts right. What's this trying to do? It's a really slow, kind of gross way of finding Sailor 6 collisions. Right, so it's looping through, that first sequence is just a bash for loop, or one way of the bash for loop. So for I in this sequence, that expands out to every number between 0 and 16 million. Echo that number into MD5, and then pass the MD5 sum into cut, pull the first 6, last 6 hex characters off, then sort and consolidate, and then when you pass that into more, anything at the top is going to be sorted based off the first column, and the first column, because of unique-c, is going to be a number. So the collisions are naturally going to rise to the top. So if the first row starts with a 2, that means that 2 things hashed to that Sailor 6 collision, or rather 2 things hashed with the first and last 6 characters. So it means that you have a collision. Unfortunately, you can't prove that you found a collision because you don't have the inputs, and that's whatever it is, pre-image 1 resistance of hashing algorithms, right? Any questions on that? I don't think anyone tried to do their homework that way, which is good because it's kind of painful. All right, last problem. I actually should have a demo for this one, but so the basic, there we go. The basic fundamental of this problem is you have full permissions for the directory, but you don't have full permissions for the file. What does this enable you to do? Specifically, you have write permissions to that directory, but not to the file. So the basic idea is you can't write to the file. You can squash the file, or you can delete the file and then put a new file with the same name. The intuition here, right, is that there is a script that pulls this and adds it in somewhere. So it just looks for a file with that name. And works with, right? So I used root instead of another user because live dangerously, right? So we can copy this out to here. It's got this. We can append our key here, and then we don't have to delete. We don't have to delete this file if we copy something over it, but naturally we can't do. Never mind, we can do that. Maybe I messed something up in here. Yeah, that's because it's owned by me. Hold on, let me fix this. I almost just graded everyone's stuff wrong again. Let's try this again. Okay, root. If we try to, this, permission denied, but we can. Let's just show. If we just copy our new SSH keys into victim. Okay, maybe I did grade everyone's wrong. Okay, if I gave you points for saying it's right, then that's a bonus. I think I messed up my. Okay, yeah. So I guess my intuition was right. So you can't overwrite it directly because that's essentially just copying to it. You have to delete this, and then, or move this into victim. All right. So sorry about that. Those are your bonus points for this quiz. Okay. Does that make sense to everyone? Does it make sense why you can't? I see some not so happy faces. Okay. Does that make sense why you can't write to the file directly, right? Basic permissions. Okay. One thing that I did see people mentioning is if you want to make it seem like you weren't even there, you can chown the file back to root. Naturally, I can't do that because I'm not root, actually, no, maybe that's a great example. So it works the same way for root. Unix systems, most Unix systems, all the ones I know of, prevent you from giving files away. This is a way of stopping people from moving files or showing files that are theirs to another user. I don't know if it's like a plausible deniability kind of thing, or like they just don't want it to make it seem like you can write something mean in an email and then make it look like someone else wrote it. I don't know where exactly it comes from, but I'm sure there's a tricky vulnerability that you could exploit if you were able to chown a file to another user. So if what users do I have on the system? So yeah, if I try to chown Postgres, this thing, it doesn't let you change the ownership to someone that you're not, to a user that you're not. Only root is allowed to throw files around to other users. All right? Okay. All that makes sense. Does anyone have any questions on the quiz?
Is there going to be a curve?
I would assume so, yeah. That would be my guess. Okay, yeah.
Like in previous years, I guess, especially on maybe like the early ones, where really problem too, where you're sort of like, what's this command? Is that sort of a common quiz type question? I guess.
Don't hold me to this, but I think this is the last quiz. I'm not sure. There might be another one when you guys get to web, but I'm pretty sure that they're more high level.
I guess I'm sort of surprised by just like, do you remember this like
yeah.
SSH?
And it's kind of archaic. Like I hadn't heard of doing that until this class. I don't think I've used it much outside of this class. It's a clever thing to know, but you're always going to have a man page. I would expect more problems in the future that are more similar to problem 1, where it's like high-level concepts or, yeah, more concepts. Yeah, and again, yeah, sorry on some of those, it's hard to give partial credit, especially when it's like a what does this? But yeah, if you do have grading discrepancies, feel free to come up after class or go to the big man in charge himself. All right. So cool. We've got 45 minutes for all the GDB you can eat. You guys did. I watched part of the video. Thank you for whoever's taking videos. That's awesome. Oh, John Black is. Yeah. So my understanding is that on last lecture, you guys developed this shellcode, right? He walked you through the process of how you get here, more or less. But the important thing is you all have working shellcode, right? Hopefully the idea that you can modify it to do something more unique isn't too far of a stretch. I'd recommend if you, I would recommend, it'll come in handy in some of the levels, modify this shellcode to just run lead directly. It's a great opportunity to kind of work through the problem yourself, understand how these relative jumps work, and how the offsets change a little bit when you change. Lead is going to be a different length down here, which means that your jumps change, but it's more or less all there. So I'd recommend that. It's cool, and yeah, there are sometimes, what's a drawback of this shellcode? This is a little more obscure, but.
It relies on standard in, standard out not being redirected.
Exactly. So if you're ever working on a problem that does something that just runs a command, but it doesn't pass standard in and standard out to your shell, this is still going to run, and it's still going to like open a shell, but there's nothing you can do with it. Well, I won't say that. It's more work to do things with this shellcode if you don't have control of the standard in and standard out. Also, it's for me, it's way more fun to just pop a shell directly, but it's more efficient to just call leak, because that's all you need to level up. All right, so some of the questions, so some people have started working through these overflow assignments where you're actually using shellcode. I think in 6 you don't need it, in 7 you do. I might not be right, but yeah. So starting at 7, and I think basically through the rest of the levels, you're going to start needing shellcode. I definitely prefer running it out of Python. It gives you some really nice features that we'll get into in a bit. But first things first, 6 or 7, one of them is kind of unique because there's a programmatic casting that happens, right? So you don't have to write anything in hex format. You can just kind of write things and let the program cast it however it needs to work with it. Typically, if you're using a buffer overflow, there's something like a string copy or a gets happening, right? And when you pass, when you just pass something like this to a gets, it's going to interpret this as a string, right? And specifically what that means is each of these characters gets expanded out to a byte, right? So this address suddenly becomes like 6666 something something 4 letters. So that's not what we want at all. The command that I typically use for this, well, actually, so Python, you can run commands right off the command line, which is nice for expansion, which we'll get into later. And I think the default on Razor is Python 2. There's still ways to do this in Python 3, but 2, the print commands are a lot shorter because you don't have to do any encoding. You don't have to do any encoding. So to print that address with Python as actual bytes, we can use something like this. More importantly, we can expand this and see that this comes out as actual hex dump. Just examines the actual bytes that you're reading off. We get these 4 bytes, and then we get a new line character, right? Now, what's kind of peculiar about what would happen if we just put this into, we overflow an address with this directly? Does anyone know yet? We'll kind of get into that with GDB. Exactly, yeah. So endian this is going to be a big problem for us. Not a big problem. It's something to consider on this. So it gets a little kind of like mind-numbing at times when you're trying to reverse this in your head, but little endian just reverses the byte order. So when we print it in, it'll come out like this, but it gets read onto the stack such that this actually becomes our address, okay? So remember little endianness. Remember to check if you're ever having issues and wondering why your address isn't working. You can either examine it in GDB and try to figure out what's going on there. You can also run it through hexdump and see if things look like they're kind of out of order or something.
So the indenness actually just changes per byte, right? Not per word.
I'm pretty sure it reads it in. I'm fairly confident that it's going to read it in reverse order. Yeah, it doesn't change the characters within a byte, but it changes each of the. this becomes in, or rather, this on the stack has to be printed in as that. And we can look at that with, let's do, we'll start with this guy. So, I think you guys have gone over this. This might look familiar. This is the kind of classic function from Aleph 1's smashing the stack paper. It's nice because it shows us calling conventions, how these get loaded onto the stack, and once we add in a little bit more, we can see how things get written into these buffers. But okay. So I'm assuming everyone's worked with GDB before, hopefully. A little bit in a systems class somewhere. If not, you're in luck, because I'm going to show you all of the tricks that I know for GDB, most of which I learned from Professor Black. Okay, so GDB is a debugger. I don't really know if people used to debug with it. It seems pretty painful to do that with, but it's great for hacking, and that's what we're going to use it for. One of the first things that I usually do is, if this isn't clear, what I just did is I loaded GDB-Q, just makes it shorter, otherwise it prints you out like a bunch of like usage stuff, or like version stuff, and then you feed it the binary that you want it to look at, so then it loads everything. And what we can do is we can look at the assembly of main and function, just so that I know and I'm not repeating things. Has Professor Black gone over any of this before? Any like GDB stuff?
He went over a little bit, yeah.
Okay. I'll be kind of brief on this stuff so we can get to the fun stuff. So we can disassemble functions, and this shows us the assembly, right? Hopefully you're more or less familiar with Intel syntax assembly. We've got our this is our prologue. We've got the epilogue. I think that's what those called. And all main is doing is just calling a function, so we get the really brief introduction to x86 calling conventions, right? So first thing to note, things are getting pushed on reverse order. I think this is in one of the slides, but function is getting called with arg1 or arg0 of 1, arg1 of 2, arg2 of 3, and these get pushed on in reverse order. So the stack will look like, these are full words because they're ints, so really it's going to be 0, 0, 0, 0, 0, 0, 0, 3, or maybe that might be flipped in order. We can find out with GDB. And then, so 3 gets pushed on, 2 gets pushed on, and 1 gets pushed on. And then we have the call function. So who remembers what call does? Call is a alias sort of in Intel for setting up a function so that we know where to jump back to when we're done, right? So we push EBP, so this becomes save saved frame pointer, and then we move ESP to EBP. So this. Then we move EBP register point up here. So this becomes, well, who can tell me what is the significance of this? This is our return address. So this is where the goods are stored. That's what we want to overwrite for this function.
Is
Um,
it a return address?
This is where this is what we're looking to overwrite to jump out of. Yeah.
Wouldn't that be?
Right.
Would it not be the saved EIP? Or
Yes. Sorry.
yeah.
Yeah. This is the saved frame pointer. This is storing the stack frame of main. It's not the return address. This is, yeah. Hopefully, okay. Right. So this is the EBP is storing the return address down here for this frame. When we push it on here, this becomes the saved frame pointer, so it's pointing to the base of the frame of the previous function. This is the return address for the function that we're setting up, the function that we're calling. Sorry about that.
I
So-
guess you switched the return address and save the frame pointer.
Mhm.
It's upside down, I guess.
Check my notes so I don't confuse myself. Yeah, yeah. Yeah, I was, let me clarify. It's always important to understand which way is up with stacks because people like to draw them differently. So these are higher addresses. Or lower. And these are higher. Yeah, okay. So, sorry about that.
I think he's still right though that you have the frame pointer and the return address flipped, maybe.
Yeah,
Yeah.
it's good. So I'll teach you a GDB trick that is how I got through this class, apparently. Yeah. Okay. Okay. Is this clear? Sorry. Let's get back on track. Okay, cool. So after we set up, oh, it's right here, yeah. After we set up our calling for this function, our next line is making room for these two buffers, right? So OX18 is, here's trick number one. So, I'll go through this command in a minute, but 18 in hex is room for 8 bytes of buffer 1, 16 bytes of buffer 2, right? And that's where we're carving out a chunk of this stack for local variables, right? And then this function's boring, so nothing else happens, and then we just return back out, okay? Did I sufficiently confuse everyone with my return address mistake? Okay, so this is a nice little trick where we can use GDB as a calculator, a hex calculator, right? So P stands for print, and whatever comes next is our format. So P. Italics, yeah. Where this is our format string. Formats are the way that we tell GDB how we want the output to be represented, right? So there's X for hex, as we just saw. There's D for int, just like in format strings. S is a C string. What's the important thing to remember about C strings?
Null terminated.
Null terminated. And I is instruction, which will be handy, handy for kind of trying to figure out it's handy for debugging. Go figure. So if we, let's go over breakpoints as well. If you want to see what the stack looks like, so we can actually look at the stack after all this gets set up, something that's pretty common in debuggers is setting a breakpoint so you can run the program and then stop it. So we're going to first set a breakpoint. Star, just like in C, is like a special character. We're saying we want to treat whatever comes next as an address, not a number. So we can pull this and set a breakpoint here. I think some versions will give you like a little flag if you have a breakpoint set. Doesn't look like we get that. Another thing we can do is, I don't know if we need this, we'll find out. We can tell it to set a breakpoint at function plus an offset. So we can set one at this no off. Hey, there we go. And we just set a breakpoint right here, right? So now, when we run until we hit this first breakpoint in function. If we give it a disassemble, disas stands for disassemble. GDB has a lot of like aliases, like shortcuts, and if you give it like one letter, it will try to figure out what you're giving it. D, there's way too many commands that start with D, so you have to go a little farther, but R is run, C is continue, B is breakpoint. So if we disassemble this, it shows us what we are. We can also run info on breakpoints, and this will show us some of the all of the breakpoints that we've set, right? If I'm moving too quickly and you want me to slow down, let me know as well, but yeah.
But the offset, is it like the line number in the program or?
Not, no, so it's not, these aren't line numbers for, you mean in the source?
Yeah.
I think that they are, I think they correlate to offsets in the actual like bytes in the machine code. So the instructions, longer instructions have more offsets. Something like a no-op only has 1 byte. So the number is actually like bytes into the program. As far as I know.
Yeah, if you look at the memory addresses on the left, that confirms it, that the addresses increment by that amount.
Yeah, good find. Yeah, so, anything else? Oh, yeah, if you're working with a program a lot and you get sick of like the 18 breakpoints that you've set because you're frustrated, you can delete a breakpoint. So if we delete 2, now it's gone. And if we continue, it runs with no other breaks, and we just exit out, okay? Pretty simple, haven't gotten to do anything fun yet. Kind of just intro to general debugging commands. Let's go into something interesting. Okay. So if we don't give it -q, we get all this information that we don't care about. So this time, main doesn't call anything. We can see GDB's handy, and it'll give us the function names, which is nice if you don't have the source code. It will, and it hasn't been stripped, it'll give you some information. So for this one, if we just run continue, if we just run run, it runs through until something, the program halts it. So right now it's hanging until we give it something for gets. So we can give it some stuff, and it just prints out and exits, right? So what we can do to try to identify what's going on, and we can calculate it over here, and with our newly gained knowledge of how the stack works, we can calculate where the overflow is going, or rather where the return address needs to be and where we can overflow it. We can also find it in memory if we give it a breakpoint right after the gets. So plus 34. Run it and give it a long string of A's. A's are what in hex? 41. Oh, it's 41. So now we're at the point where we want to examine the stack, right? So my base is always EBP. It makes it kind of easy. You know where things are. If we want to look at a register, just like how this treats the next thing as an address, the $ is going to treat something as a register. Okay. So if we just try EBP minus 40, it doesn't know what EBP is. It's trying to run it as a command. However, if we do this, that's not much better either. Right, we're going to examine some memory. Oh, what a great segue. Okay, so this is print. This is useful for calculations. If we want to use X, it examines things, which is super handy for trying to read the stack. So this one has 3 identifiers. N is just number. F is, guess what? It's format. And U is unit. So this introduces another thing for us to remember. All of these are formats. Units are pretty similar. We've got B for byte. So that's going to give us 8 bits. Keep in mind these are sizes, so you can represent a number of bytes, a number of any other of these as formats. So this is just the amount of memory that you want to look at. /H is half word. This isn't super useful, but, well, I shouldn't say that. I haven't used this much. Your favorite one is going to become W for word, because we're in 32-bit memory, and everything is a word. Addresses are words, ints are words, so that's super handy. And if you ever go on to the big scary world of 64-bit, you're going to be using giant words, which are how many bits?
64.
Exactly, yeah. Cool, okay, so now we're all set for trying to find our address in memory. So we can do examine, let's just pull, for example, 40 words represented as hex, and we're going to start from EBP minus 40 hex. So I don't see any 41s, and it's easy enough to just keep looking. Oh, that was not the right. There we go. So all the way up here are our 41s. If we want to find the start of it, we can just keep going. But instead, let's go ahead and do something a little more interesting. So we're going to pull our shellcode in here. So we've got our shellcode here. We can just print this in, but then we're going to have to fill up the rest of the address space with bytes. So instead, to make it a little easier to find out where we are, let's add some variables in. So our buffer size is 256. Now this is just the size of the buffer. We're going to have, I think it's, it should be 4 or 8 more. I've had some weird kind of issues trying to calculate directly, so I think I might be missing something that happens in the stack, but we can use a little trick to get around that. So we've got our buffer size. We'll have a return address that right now we'll just set to what's a really obvious one? 8. Why not? And our shellcode. Okay? So now down here we can do print I guess we can probably just do this. Print A times buff size minus the length of our shellcode. So that's going to print exactly what it sounds like. It's going to fill the buffer up until we need to put our shellcode with A's, and then we're going to actually print our shellcode, and then after the shellcode, we're going to put our return address. Okay? So the return address, we're obviously expecting these 8s to just show up in memory, and then we can find wherever our shellcode lands with this. Hopefully, it's right before the return address. So okay. So we'll go ahead and set another breakpoint right after the gets, so that we can figure out what's going on, and then hopefully this works. This is called shellcode. Okay. So here's another trick. We can print this out. So first off, if we just print this, we get a bunch of garbage. But we can redirect this to a file. Then in GDB, if we yeah, GDB doesn't work so well when it's not running on binary. Fun fact, there is PyGDB, which does this for Python. Although buffer overflows in Python are not something I'm familiar with. So now, instead of running the command directly, we can just give it the file. So we see enter something, and it's redirecting input from that file that we just printed our exploit to, right? So we're going to do the same thing, extract or examine, 40 is a happy number, 40 words from EBP minus, this time we should be pretty close. So we'll do minus, actually let's just do 20. Oh, no, that's not it.
You don't need disass at the front there.
Oh, of course, thank you. Yeah, don't do that. Okay, so here we see our return address. If we do, we can see that this is EVP. This is our return address, or excuse me, this is what we wrote as our return address. So this is actually the main's frame pointer. This is the return address that we're looking at. And these are the arguments for me, which we'll get into in just a second. But, so what does that mean? It means our shellcode starts somewhere up here. So if we do this again, a little higher up, we see our A's, right? So A's run all the way up to the start of the shellcode. And we can confirm that, but with a little bit of 40 instructions. So if this is 28 and we have 2 bytes of 4s before it actually starts, we'll go ahead and do a plus 2. And hopefully that works. So hopefully this is a little familiar. We've got our relative jump, all of the goodies to set up our registers, how we need them to, and then we should see an int 80. Yeah, int 80 right here. All right, sweet. So xi examine as instruction, and it takes the number of things. Easy way to, or convenient way to figure out what Or, yeah, you can use it to examine memory as instructions. Cool. So if we continue this, what should we see? We're going to need a seg fault. Are we going to jump to the 8s? So I don't actually know, but my prediction is we're going to pop this out, which is the 8s. This gets popped into what I believe. I think EBP, right?
Yeah.
It's the reverse of the calling. So push EBP, move ESP, EBP. Yeah, so we're going to pop EBP, so this gets popped into EBP. And then we jump to this return address, which we haven't touched yet, right? So we're not going to see a seg fault right away, but I think we're going to see a seg fault after we try to make use of that EBP address. So we just continue. Here we get a seg fault. We can use info registers, and we see these 8s in EBP. So after those get popped out, it tries to do this. Let's see. Just out of curiosity, what if we do that? Nothing. Okay. Well, we do get a seg fault. It's obviously not what we want, right? We're looking for our return address. So where did we print out these? If we pull this and get lucky, let's see here. So we want 28 D7 FF. Now we have our dead weight as well. Let's see if we can just get lucky.
Sir,
Mhm.
what's the dead weight for?
Oh, sorry. So back up here, our dead weight is, we haven't moved this at all, right? We just added the return address. So I changed the variables. This is now called dead weight. It's still in the same place in our buffer, and it still has the same value, but now we've added in another value that's going to get written into this place, right? So this is dead weight. Yeah, doesn't really matter anyways. It's just 4 bytes. So if you can't read it, don't worry, the program can't either. This is going to be our return address. And hopefully, this points at the start of our shellcode. Simple. Yeah. And bummer. Okay, well, we're going to see if we can debug this. So that's why we're here, right? So, same thing. So this is one of my most, this exact command string is one of my most used, and hopefully we'll have the opportunity to get to that. We're printing 5 words from EBP, right? So this is printing EBP, which we don't really care about for this class, the return address, and then whatever comes next. Really valuable in main, less valuable, well, this is main, so less valuable right now, but we can get into that. So these are our 8s still. This is our return address. Oh, that's why, because we didn't add 2. If we try this again, no, that's just not quite right. Let's see if we can identify where our stuff is again. Let's do this all over again. So here are our 4s. Here we go at 18. Oh, maybe I just pulled the wrong address. So sometimes, well, we'll use this as a segue and pretend something else happens. Sometimes the address changes between runs. And sometimes you're like me and you just mess it up. But why not take advantage of this big buffer that we have, 256 bytes minus the 42 for our shellcode, and put something a little more useful in it, right? So A's, if we jump to A's, the program's going to say, I don't know what's at this address 414141. It doesn't look, or I don't know what this instruction is, 414141, but I don't know what to do with it, so stop telling me to work with that. Instead, we're going to give it our friend Mr. Noah. Two handy things about Noah. Well, so what's the most important part about a Noah? Why do we care that we have a Noah and not an A?
If we happen to start our, like, if we happen to point somewhere in the middle of a bunch of no ops, it'll just run through those no ops, then eventually run
Exactly,
it.
it's an instruction, right? It knows how to run that, and it's, I don't know how else to say it, it's a no op, so it doesn't do anything. It just slides right down. That's what we call the no op sled. Second most valuable part of a no op, besides the fact that we actually know what to do with it, it's only 1 byte long, so you don't have to worry about landing on the right byte. You can land on any byte and it's going to do the same thing. So now instead of A's, we have no ops, pretty much just as easy to identify in memory, so I'd recommend using them all the time. Our return address, that wasn't, our return address was somewhere in here, but we actually have a ton of no ops now, so we can just do some guesswork. Let's take this minus maybe 30 hex off the top. So we've got this. So that's going to make our address still FFFF, D7, and instead of 28 or 08, let's go ahead and decrement this to 6 and make this D8. That should be enough. Does that make sense, what I just did? So I just subtracted an arbitrary amount. In reality, what you can do is go back into your program, load it again, load your whole sled, and just pick whatever's in the middle. That'll give you the best chance, without doing any kind of calculation, of if something changes in your environment when you're not running in GDB, you'll still land in the normal sled. So now, and I imagine we got a shell. But let's run it through GDB, just in case, because it'll be a little more obvious. File. Oh yeah, and if you do what I just did and forget to load something, you can always just tell it you want to use this file now, and then we run it like this. Okay, here we go. Executing a program bin dash. So the reason that didn't change in here is because I have a prompt that gets loaded in because it's loading my shell from my user, right? But in GDB, it tells us explicitly that we're running this, okay? So keep that in mind if you're running these somewhere else and something weird happens and it looks like you may not have actually triggered your shell. You can run it in GDB and find out. Does that make sense with the no ops at least? Okay. So as we already learned, I'm not the best and brightest at getting my calculations right on the stack or really just knowing what's going on. So I actually have another trick that I use, where you get really lazy and you say, okay, well we're throwing in a ton of no ops. We clearly don't care that our shellcode doesn't exit cleanly, so we don't care what happens to the stack after we do our business. So why not just throw in a ton of return addresses and hope that one of them works, right? Now this is super lazy, and the reason that it works kind of cleanly is because we're in 32-bit. If you move to 64-bit, just while we're talking. If you move to 64-bit, this doesn't work as well because there's alignment issues. So keep that in mind if you ever move on to bigger and better things. But for the purpose of 32-bit, you can be really sloppy. And so just to make that explicit, now we're blowing through main, or the main frame pointer, the return address, argvc, and argv.
Parameter.
argv, yeah. argc,
No,
that's it. argc and argv, right?
Those are just the parameters that main
Yeah,
have on that.
but for main,
whoa.
it's going to be, the parameters that get passed to main are argc, argv, and p, right?
Right, but if we're going off the stack there, those
Sorry,
are yeah.
So for, this is the stack for function
Right.
from before, so not to make things more confusing with this now immortalized on camera stack frame, but yeah, so main, we don't have a ton of time, but I'll try to take us through that. If we do, just to show that it works, we didn't do a segfault. That's the thing we care about. If we do GDB, file this again, we'll get the dash. Cool, dash. So real quick, just to illustrate what I was just talking about there, let's go back to simple args. We'll do, let's break it main, run, and now we're in the main function, right? So if we disassemble, we see we're here. We see we're setting up the frame pointer. However, if we do, once again, favorite command, definitely remember this. Now we can see the return address or argc. So for this one, we've got return address is the saved frame pointer is 0x0. Our return address is here, and then we have argc, argv, and p. Okay. So, well, what are these, you ask? Argc is the counter. It tells us how many arguments got passed. If you don't pass any, it's going to be 1 because the first argument is, I don't know, GDB. Let's find out. If we look at it as a string, check that out. It's the program that we're running, right? So examine as a string, not the address, but whatever the address is pointing to. Argv is an array of pointers. So if we have more arguments, we can actually give it a number of strings or a number of things to examine, and it'll just run it down. And we can check that out right now with, let's do 20 strings. What do you think this is going to print out for us? Yeah, and because S is treating things as C strings, it's going to iterate over the environment, parsing on null terminators. And now we get all of the goodies that I've stashed in here. So let's see. One last thing that I guess it's pretty much time to go, right? Yeah. One last thing I'll leave you guys with. This is one of my environment variables, right? It kind of has this innocuous name, capital S, capital C. Who knows what that is, but it's probably not standard, right? If we look at some instructions, not as that, we see a bunch of kind of no-ops. That's interesting. We can continue. Oh my god. Okay. We're gonna actually, I'm going to be a little more smart and try to calculate this. Okay. Yeah, here we go. Repeats 180 times, so let's do 40 instructions. This plus 180. Let's see what happens. Cool. This looks kind of familiar again, right? There's our int80, our good friend int80 invokes system call. So the reason that I have this loaded in here is because your stack is, well, your stack changes, your environment changes as well, but now I don't have to pass the shellcode in as an argument. A lot of times you'll be able to, unless the program is doing something funky where it's checking arguments and canceling out early if you have too many or too few. You'll have to pass your shellcode in some other way, right? So the important thing with overflows and running shellcode in general is that you just need what you want to run on the stack somewhere, right? That can be an argv, that can be an envp, that can be in a buffer that you write to directly with some string copy or gets, right? Okay. So you don't have to put it in your environment. I think there's probably some times where on Razor where you'll find it beneficial, but maybe keep that in mind. The other thing, so remember on Razor, we don't care about being stealthy, right? You can like smash the stack all you want as long as you get what you need. That being said, you also don't really care what's in the buffer. So if you have like a 64 kilobit buffer, may as well just fill that with 64K of no-ops, right? It's not always going to make your, it's going to make your life easier. It's not always going to be the only solution, but it can make your life a little easier where it gives you a lot more room to play with. So keep that in mind. The other thing is GDB does mess with your stack frame, especially on level 12. Has he talked about level 12 yet? Infamous level 12? No, okay. Well, yeah, you're in for it with that one. Level 12 is a fun one, but it is, I think it's the only level where you do need to be byte perfect, which is painful. It takes a lot of time. Keep in mind that GDB will mess with your stack frame, so that's why the no-ops are helpful, and any chance you get, make your life easier, give yourself a fat sled, maybe throw in a couple of return addresses, just gives you a lot more room to play with. But keep in mind, don't be like me. Try to remember what's going on. Try to figure out what ESP is. Keep an eye on the stack frame. We overflow things from the top down. So if there's an important variable somewhere up here, or an important string somewhere up here that is being checked or used somewhere in the program, and we burn right through it, that's going to throw off the program execution. So try to remember where things are on the stack. You can always use GDB to try to figure out what's going on, see how counters are incrementing, or see where strings are getting checked against. But yeah, I think that's all I've got for you guys. If you have questions about GDB syntax, let me know. I know there's a lot there, but you guys are going to learn way more by just beating your head against GDB for 4 hours than from me lecturing. So just go at it and get some practice. All right, thanks.